So thanks everyone for coming. I guess we're already late and I'm between you and lunch, but I'm going to take the full 20 minutes anyway. Okay, this is a joint work with Srinivas Kudikar and Rudiger Banki. The program only lists my name, but this is such a well-organized conference, I'm sure it's my fault. I just don't know how that happened. But we have a paper which we posted to the archive. You can see it here if you want to get any details. Okay, so let me first just state exactly what the result is, just to be clear. So by universally, we really mean binary memoryless channels. So we're looking at binary codes. And essentially, the statement will go something like this. If you pick a capacity between 0 and 1 and consider all binary memoryless channels with capacity at least C, then we can communicate reliably with this spatially coupled ensembles within epsilon. And with high probability, if you pick a membered ensemble, you can get to within epsilon. And the nice thing about this is that it's true for all channels simultaneously. And so what I'm going to try to do in the talk is to give what I think are sort of the essential reasons, mathematical reasons why we can prove this and why it happens. Now, there's a history behind spatially coupled codes, which really goes back to low-density parity-check codes, convolutional parity-check codes. And I have to say that when I first heard the results about the improved thresholds of these codes, I didn't believe it. So around 2005, people were claiming that just with a 3-6 structure, you form a parity-check code, and in the convolutional style, then the thresholds improve. I didn't understand why that could be. And now I think I understand it, but it's still quite subtle. So here's a list of papers. I'm sure I'm missing some. There's been a lot of work on these structures. People have found a very good performance. Last year, we were able to prove capacity for the binary erasure channel, and essentially the similar ideas can be applied to general case. Okay, so spatial coupling, we know, has been applied to many other areas, and it's actually a very powerful phenomena. And part of what I'd like to get across in the talk is maybe that some of the ideas that we developed for the coding setting are actually more general. So in particular, it was applied to compressed sensing, starting with Kudikar and Pfister in 2010, and recently in a paper by Donahoe, Javin, and Montanari, they were able to prove that a sort of spatial coupled construction can achieve the L0 limit for compressed sensing, so optimal performance for compressed sensing. Combinatorial problems, KSAT problem. Our chair has worked on using spatial coupling for multi-user detection for CDMA. I'm not going to talk about it today, but we also have another set of results on 1D spatially coupled systems. And for those systems, we know how to essentially solve everything. So for this case, we now know how to prove the spatial coupling phenomenon actually works the way people observe. And Cepheid-Wolf problems, multiple axis channels, so on. Okay. Okay, so let's go back to the LDPC case. So this is a typical LDPC graph, and we all know how we construct the ensemble. We pick some number of variable nodes, some number of check nodes, form a bipartite graph, permute the edges at random. We captured a large-scale structure in this sort of prototype picture. So the prototype is representing the macro structure. Here we have a check node of degree 6 and 2 variable nodes of degree 3. This represents the 3-6 ensemble. Now, the spatial coupling idea is to make this bigger, and essentially you think of it this way. So we can think of many, many copies of the LDPC graph. Here we see a bunch of them sort of oriented vertically and distributed in space horizontally. Now, if we just connected everything at random, it would just be a huge LDPC code, and we'll get whatever kind of behavior we expect out of such a large code. And the trick in the spatial coupling is actually to restrict the connections to one dimension. So the fact that we're restricting them somehow changes the behavior and helps the overall performance. And that was one of the reasons why I didn't really believe it in the beginning. I didn't see how a restriction like that could really help. But we identified 2 dimensions then. So one is the horizontal and the other the vertical. So the size of the system, the vertical dimension, we'll refer to as M. Okay. Now, if we, in the picture I just showed you, if we only connect edges vertically, in the photograph vision of the world, it looks something like this. We just have a bunch of parallel structures, all disjoint. Each one of them has the same sort of macroscopic structure, but there's no connection between them. And the spatial coupling, we essentially introduce sort of local interactions. On this picture, I've actually abused the protograph construction because I didn't really mean these to be degree 6 variable nodes. Really, I want to think of them as just degree 3, and the edges coming out of them represent, say, a probability of connecting an edge. So the idea is that you take the edges in the original disjoint picture and just kind of spread them out randomly. So you connect them to some of the neighbors over some width W at random. And for now, we can just think of it as uniformly random. So two key parameters that come out besides the M I showed you earlier is the length of this overall structure, which we create by just terminating beyond a certain point, or just eliminating all the variable nodes outside some region, or equivalently declaring the channel to be perfect and known there. And the other parameter of interest is the width over which we do the spreading. Okay, so both of them play an important role in the analysis. Okay, so how do we get to capacity? So what I claim is it's really a tale of 4 limits. And the first one is the degrees. So we're going to focus on regular ensembles. And so essentially we can think of a degree once we pick a rate for the underlying ensemble like a half. And we're interested in the rate, say the degree of the variable node. And in order to get to capacity, this has to become large. Okay. Second is this component side. So the vertical dimension M, that has to go to infinity. Now that has 2 effects. So first of all, it reduces the problem to density evolution analysis. And the other one, which is maybe more subtle, has to do with property of trellises, that you normally in a trellis of any finite dimensional size or finite dimensional state space, over length, dependency on terminating conditions decays. It's a sort of fundamental result in ergodic theory that no one-dimensional structure exhibits a phase transition. Or another way of saying that is that in one-dimensional structures, if you have finite-sized state space, then a dependency on, say, terminated condition always decays. However, when the state space goes to infinity, this may no longer be true. And this is actually essential to this spatial coupling phenomenon. Okay, third point is that we let the block length go to infinity. Okay, this has 2 effects. So one is rate loss. So we saw some on the earlier talks, and I didn't mention it in the slide, but at the very end, because of the way the graph is terminated, the rate of the spatially coupled ensemble is actually slightly lower than the underlying ensemble because of the endpoints. But if the length is very large, then this difference in the length goes to 0. The other thing, which is maybe more mathematically important, is that when you look at the infinite spatial coupled system, you have translation variance in the underlying system, which makes it sort of easier to analyze in some respects. Okay, and the final point is the spatial coupling width. We also have to let that go to infinity, and this essentially takes us to the continuum limit. It has to do with sampling. So in space, when we work in a continuum, we can sort of achieve capacity exactly. The discrete systems that we actually use, we can think of as spatially sampled versions of those, and we actually take some loss for the sampling. Okay. So I'm actually going to dwell the longest on the limit, which is actually least essential, and that's this one here. And in order, because I'm going to use this to sort of lay out the problem and how I think about it, or how we think about it. Okay. So I want to introduce 3 concepts: exit functions, the area theorem, and generalized exit functions. Okay. So I assume people are all familiar with the usual exit chart representation of iterative decoding. So here we have exit chart for 3,6BEC. So the blue curve is the variable node curve, and the red curve is the reflected check node curve. And density evolution corresponds to alternating evaluation of these 2 functions. So we go horizontally to evaluate the red curve and vertically for the blue one. So here we are below the map threshold, below the BP threshold, and if we iterate, we go down to 0, 0, which is perfect decoding. On the right, we have another example of the exit curves. Here would be above the BP threshold, and so here we have the the fixed point at which BP would normally get stuck, and there's another unstable fixed point in here, and one in here. So this region in here, shaded in gray, is the part of the region that dominates the behavior in the spatial coupled system. And you have to understand what's going on in this structure in order to understand the spatial coupled system. Now this is a 1D example, and I'm going to use some sort of 1D pictures like this to help explain what's going on. But in the more general case, we're looking at not real value functions, but density valued functions. Okay. So I want to describe quickly the exit function. So the exit function was introduced by Ten Brink in 1998. This is a tool for looking at iterative systems, a design tool. And essentially, one way to think of it is just a model of density evolution. So you think of a code, for example, a single parity check code, and you have some observations for the bits in those codes, and the exit function essentially is measuring density evolution, which is saying how much information are you getting about one variable from the others. And this is expressed using entropy. So you look at the conditional entropy of one of the bits given the other observations, and that information is coming from the structure in the code. Now we can look at the average over the code of the exit function, which we have represented here, and that turns out to have some interesting properties. So besides being a nice tool for design, it also turned out to be an important analytical tool for analysis of the binary erasure channel. And the key thing here is the area theorem, which was proved in 2002 by Kramer and Ten Brink. And what it says is that if you look at the area under the exit function, what you get is the rate. So, for example, for the parity check code, here's the exit function curve here as a function of the channel erasure probability here, and the area under that curve is 3/4. Okay. For an ideal code, for a perfect code, the exit function would look like this dash curve here. So, let's say a rate 1/4 up to, if the erasure probability is below 1/4, you get essentially 0 entropy, meaning you have perfect decoding, and then you'll hit a sharp threshold where it'll go up to 1. So we know that any code has to preserve this area condition of 3/4 if it's a rate 1/4 code, and an ideal code then would have to look like this. Okay. So it turns out that the area theorem for the BEC has essentially trivial proof. It can be reduced to the fundamental theorem of calculus. Now, I don't want to go through the calculation, but the basic point is that you just look at the conditional entropy of a code word given the observed variable and differentiate with respect to the channel parameter. And for the BEC, what you get is exactly the exit function. Now, the exit function was used not just for the erasure channel, but for general channels. But, and it always seemed to sort of satisfy the area theorem, but it wasn't quite satisfying it. Now we understand why. This last step here in this derivation, going from this derivative to the final line, only works for the BEC. So the correct generalization of the exit function, if you want to look at general channels, is just stick with the derivative of the conditional entropy. And if we look at that functional average over the code, we call that a generalized exit function. And it has some nice properties. In particular, it will automatically satisfy the area theorem. Okay. Now, for LDPC codes, in fact, we can look at the generalized exit function for LDPC codes. The only issue there is that when we actually decode the codes, we use the belief propagation algorithm, whereas the formulation just says what's the conditional entropy. However, it's possible to connect up to belief propagation decoding by looking at the tree. So if we look at an infinite tree, for example, and looked at its generalized exit function, we could concentrate on the contribution given by the root node. If we let the tree go to infinity in size, then what we're going to pick up is essentially BP type behavior of an LDPC code. So not to dwell on that too much, let me just give you an example. So here we see what we call the BP generalized exit function. So this curve represents if you like, at least this part of the curve. I don't know if you can see the green dot, but it's the top part of the curve coming from here down to this point and then straight down would represent, in some sense, a contribution to the generalized exit function from that root node in an infinite tree. And each point on this curve corresponds to a fixed point of belief propagation. So we've illustrated that here with this one dark point here, and then two densities which represent, for example, the channel density, in this case the Gaussian channel, and the density being emitted at a variable node according to density evolution. So the entire family of fixed points of density evolution we think corresponds to this larger curve here. And if you integrate that curve across the entire channel, you will in fact get the area condition. So the area bounded by this sort of curve here, including this branch here, which normally you wouldn't see because it's coming from the unstable fixed points of density evolution, this area corresponds to the rate of the underlying code. Whereas the BP exit curve, which looks like this, strictly speaking, does not satisfy the area condition. Okay. Now, so here's one analytical result that is in the paper, which I'm not going to derive, but let me just say that we know how to integrate the g-exit function, the BP g-exit function. And essentially, if you integrate across the top of the curve, you get an expression that looks like this. So you get one term which corresponds to the rate, and you get another correction term which depends on the fixed point associated to the density evolution at that point. So x here represents the density coming out of the variable node according to density evolution, and there's some formula which is some entropy functional related to that density that determines essentially the area under the curve up to that point. So, for example, if we look at the point along the curve where this area term equals 0, then we know that the area under the generalized exit function up to that point is equal to the rate of the underlying code. And we actually, it's conjecture that this is actually the map threshold of the underlying ensemble. We know that's true for the binary erasure channel, but not in general. So we can just define this threshold. We call it the area threshold. We know in general it's an upper bound for the map threshold, and we think it's conjectured to be equal. Now, it turns out that what we want to actually show is that spatially coupled systems essentially achieve this threshold, the area threshold. And to see why that happens, let's look at the generalized exit functions, BP exit functions computed for the spatially coupled systems. So here we see the BP generalized exit function for the 3-6 ensemble. Now, if we add the area threshold, this then would represent a conjecture for the true generalized exit function for this ensemble. So if it's true that so I should maybe elaborate a little more. The conjecture is a little stronger. It says that along the top of this curve up to this point, we conjectured that the BP, oh, thank you, which is the top button. This one? Oh, thanks. Okay, so the idea is that this top part of the curve here actually corresponds to the true conditional entropy of the underlying LDPC ensemble, in which case the shaded area here would correspond to the true generalized exit function of the underlying ensemble. Now we can look at the spatially coupled system for some set of parameters. So this is L equals 4, 8, 16, 32. And you can see what seems to be happening is that that curve seems to be converging to the boundary of the shaded region. And that's essentially what happens in what we need to prove. Okay. So maybe to get a better view of what's going on, I can show you what the fixed points look like. So this is a little animation, and you have to pay attention. So this curve here, the dark black curve, corresponds to the BP fixed points, and the shaded one corresponds to the spatially coupled fixed points. And what we see, Okay, there it goes. So this is the part you need to pay attention to. Okay, I'll show it again. Okay, so watch what happens when the black dot goes vertically down. Okay, so first of all, you can see it's essentially going straight down this line, which corresponds to the area threshold. And I want you to pay attention to this curve here, so you can see what's happening. So what that curve represents is essentially the fixed point densities of the underlying spatial ensemble. Okay, it's half of them because of the symmetry and because of space we're showing 1/2. It's actually, if you want to do the whole curve, it should be reflected and copied. This part here is the channel. So these are the fixed points of the spatial ensemble that give rise to its generalized exit function, the BP exit function, which is this curve here. Okay. Now, so finally I get to the point of why do we need large degrees? Well, the hope is that the spatially coupled system will go to this area threshold. So if we want to go to the Shannon limit, we need the area threshold to go to the Shannon limit. And if we look at large degrees, this is what happens. And it happens universally. So this is an example binary symmetric channel for essentially 1020 structure. And you can see that this area threshold, what we conjecture is the true underlying map, generalized exit function, is essentially ideal, corresponds to an ideal code. Okay, so that's what we need in order to get the capacity. So that's why we need the degrees to go to infinity. So we need degrees to go to infinity even for the map threshold to go to the Shannon limit. What we get is the area threshold goes to the Shannon limit, and now we can forget about this and focus on achieving the area threshold. Okay. Okay, so I want to again look at the remaining limits. So one is the component size going to infinity. This is critical because it allows us to reduce the modeling of the system to density evolution. The other thing is that by going to infinity, we lose decay of dependence across the spatial dimension. And once it reaches infinity, we can have infinite length correlation in the model, which as you'll see, is essential to the performance. Okay. Next limit is the length going to infinity. As I mentioned before, we need this to get translation invariance and to get rid of the rate loss. And the fourth one was the spatial coupling width going to infinity. This gives us a continuum limit, and so we avoid what I call sampling loss, spatial sampling loss. Now, in the limit, after we take all these limits, we get this kind of simple iterative function space understanding of density evolution. So here I'm just showing the LDPC case. Okay, so I want to think of, roughly speaking, variable node, check node. And what we have are two functions, which is update densities. So, for example, this H superscript F here represents a variable node update. So we have a density which comes in as a function. We apply some function, maps a density to a density that's X, and then X goes into another function corresponding to the other node to get Y. So these two equations just represent sequential updates of the two functions that come from density evolution of standard LDPC. And the channel's hidden in here, doesn't really matter. The thing I want to draw your attention to is the connection to the spatial case. So the spatial case is essentially the same, except instead of having a density, we now can think of the infinite real line, and we have a density at each point on the real line. And so we have not just a density, but a function on the real line, each point of which gives you a density. And the equations look almost the same, except that before applying the updates corresponding to the nodes, we do a spatial smoothing operation. So we take the spatially distributed density, do some kind of convolution with a smoothing operator, think of just local averaging, and then we apply pointwise this update to get the next function, and this just iterates. And this kind of mathematical structure will be the same even in the discrete case. So the discrete case we'll just think of as sampling this picture. So here we have, the idea is that we have infinite real line with densities on them, some kind of smoothing operation to give us the input to the other side, and then pointwise update, smoothing, and so on. Okay, so what we want to understand is what this structure can do. Okay, so from my perspective, this is the main mathematical point right here. Okay, so LDPC thresholds, and that's true even for the coupled ensembles, are characterized by their fixed points. And in particular, the thresholds are characterized by the existence of fixed points. So typically what happens, if you're above the BP threshold, you start decoding, you get stuck in a fixed point. If you improve the channel, the fixed point moves, and you can trace out essentially this curve that we saw in the g-exit function. And once we hit the BP threshold, it disappears, and then we get successful decoding. Now, the infinite spatial system, if you look back at the equations, any fixed point of this system will give me a fixed point of this one. Or all I have to do is set the corresponding functions to the constants. So the spatial averaging, of course, if it's a constant, will just give me the constant. So each fixed point of the underlying LDPC code gives me a fixed point here. But the main thing is that in the spatially coupled system, there emerge a new set of fixed points. And these are different from these other ones. And the way that they're different is critically this, that they're not constant, but they only exist for a critical channel parameter. So let me show you how that works in the 1D case. So here, I don't know if you caught that, but I initialized the system with a step function. Here we see essentially the exit charts corresponding to the update. And what's happening is we're just iterating, updating the two functions. And you can see the two colored shaded areas, and if you could measure, you would see that these two areas are the same. And so we have some kind of balance condition here. This is, for the BEC case, this will correspond to a map threshold type condition, and the behavior of the system is we get this fixed point. So this curve, you used to think of going off to infinity. So the top is 1, corresponds to this point up here. The bottom 0 corresponds to this point down here. And this kind of behavior only happens when we have exactly this type of balance. If we perturb it a little bit, for example, this, then what happens is we no longer get a fixed point, we get a traveling wave solution. And in the 1D case, we actually know how to find these solutions. And what will happen is that the system will converge to the constant fixed point I mentioned earlier corresponding to this fixed point. Similarly, if the balance goes the other way, we get the same behavior, only the waves go in the opposite direction. So we'll converge to a constant fixed point like that. Okay, so here's sort of the summary. So even in the general case, we can show the existence of these infinite fixed points, but they have to have certain special properties. So it has to be the kind of area balance. And what it turns out is that the infinite fixed points, if you look at the two limits, they have to satisfy some special condition. And in particular, this A functional to define the area threshold has to be equal. And so what we get is essentially that something like an invariance principle holds for these fixed points. They can only occur at very special values of the channel. In particular, for the regular LDPC case, what we show is that when one limit is essentially perfect decoding, the other limit has to satisfy this condition A of x equals 0, which is the area threshold. So corresponding to this balance of the two colors, in the general case, what we get is that the channel has to be at the value at which we get the area threshold in order for this fixed point to exist. Now finally, I just want to try to give some indication of how this connects up with the generalized exit function. So if you think of this as the infinite fixed point, and what I'm going to do is take a little window and slide it over, and from this construct, in essence, something very close to the family of fixed points we see in the g-exit picture. So what's happening is that this spatial infinite fixed point gives us rise to a family of fixed points for the finite ensemble that corresponds to that vertical part of the g-exit curve, and it has to happen at the area threshold. Okay, so that's the reason why we get the area threshold. Okay, so just to close, so the critical thing is that we get the spatial fixed point can only exist essentially at the area threshold. From this, we can construct this G-exit picture. And if you upgrade the channel beyond the area threshold, such a fixed point cannot be supported. And therefore, because we have the termination in the spatially coupled ensemble, it can't support any fixed point other than the one at perfect decoding. And that's the end of the story. Okay, thank you very much. Okay, I don't know how much over I am. I must be over. No questions? Okay, good. Everyone's hungry. Thank you.